So, hello everyone. My name is Ed Sharp. I am a final year student at UCL. So my PhD basically attempts to address the question of how domestic demand for electricity will change in Great Britain if it becomes more closely linked to weather through the electrification of peak demand. Alongside this, I'm doing a demand-supply model. So it looks at in the same weather system and uses weather-driven supply to look at how that will vary over space and time in the same context. So to investigate this, I've wrote a model that can simulate both at a half-degree spatial scale. The scope of this model is shown in the animated plots there, and it can run hourly anytime between 1980 and 2010. So the primary driver of this is climate reanalysis, which is provided at the scale shown in these plots. That allows it to be simulated at this scale. So, alongside the reanalysis, there are a lot of other drivers that go into the model, including population distribution, building stock characteristics, energy use patterns, and development restrictions on wind farms and possibly solar farms. So in order to demonstrate the structure of the model and the purpose of it during the PhD, I just created a simple scenario which I've run over 2010. And it's the same as shown on the poster as well, so you can see a few more details of the way that's analysed on there. So using 2010 as the base case, I've simulated the installed capacity of wind during that year, but to this I've added 5 offshore wind sites, each of a gigawatt in capacity at the locations shown there. The circles are the onshore wind farms. The offshore wind farms are basically arbitrary locations designed to show how the model works and add a greater level of spatial diversity in, as well as double the installed capacity. However, the intention of the eventual modelling is to introduce realistic spatial scenarios of wind. For example, populating round 3 zones. So the output of the supply side of the model is shown in the top animation. You can see there that there's greater consistency in the offshore wind farms in harnessing the wind resource. You can also see the larger capacity, which is obvious. You can pick up weather fronts if you look over a longer scale, but generally you can see the sort of chaotic nature of weather within that. But like I said before, I'm doing demand and supply, I'm doing both sides. So alongside the supply scenario in this, the map shows some of the data that goes into the demand side of it. So in this case, it shows the percentage of housing that is detached in a particular area. And the demand model then goes on to measure specific heat loss parameters per building type. So you can then do that, the same unit area for that. The scenario here, however, just for simplicity, doesn't increase anything within that. It just shows the normal demand that's standard for 2010. It's very clear the difference between the two. You can see a more regular beat, and you can see the diurnal peaks and troughs. That's the big ones during the day, and then it goes down during the night. You can pick out centres of demand. You can see London pretty clearly in there, and you can see with the other big cities in the UK. So the next slide, what I've done is to show how the two are compared, taking demand away from supply. So the plane is at 0, and where demand outstrips supply is negative, and where where supply outstrips demand is positive. So you can see it's very clear from here that demand is almost of a greater magnitude. There are fleeting moments of areas with greater supply. You can see in Scotland there are tiny little bumps where you might have a bit more output for that particular area. the bottom graph shows how when you aggregate this, it's of a totally different scale. So yeah.